Hi folks, welcome back to the last video for known cross-sections practice. We're going to take a look at questions 5 and 6 in this video. Question number 5 says, a parallelogram with a base in the xy plane and a height equal to twice the length of our base is our cross-section. And once again, we're looking at our functions f of x equals the square root of x and g of x equals the negative square root of x. And let's go ahead and draw a more traditional diagram, okay? So we've got our y-axis, we've got our x-axis, we've got our square root of x, and we've got our negative square root of x. Now this time, our stopping point, I've decided, is going to be 25, 5, and then this point down here would be 25, negative 5. All right, so let's take a look at the cross-section. The cross-section is a rectangle or a parallelogram, and this is the base of the parallelogram. And so when I draw that sample cross-section on my diagram, I get something like this, okay? And that green line represents the base of the parallelogram. Now, if we want to think about setting up our equation, okay, we're going to get volume equals the integral from a to b of the area. And because my bases are perpendicular to the x-axis, I'm going to have a dx. All right, let's fill in our bounds, but also think about the formula for the area that we're going to need. So the integral from 0 to 25 of the base times the height. So a parallelogram is very similar to a rectangle in that we can find the area using the base times the height, and we are lucky here because we have the information about the height. We know that it is equal to twice the length of the base. And we know that our green line represents the base of the parallelogram. So we get the integral from 0 to 25 of this base is 2 root x. We've seen that before because it's twice the distance from the square root of x. And the height is going to be 2 times the base. Because again, up here it says that it's equal to twice the length of the base. All right, let's clean this up. We get 2 times 2 times 2 is going to give me a constant of 8. The integral from 0 to 25 of square root of x times square root of x is x dx. All right, let's integrate. 1/2 x squared, plug in 25, plug in 0. That's going to give me 4 times 25 squared minus 4 times 0 squared. This goes to 0, and then I end up with 4 times 25 squared, which gives me 2500. And this represents the volume of the shape when cross-sections are parallelograms and I start at 0 and I end at x equals 25. All right, we've got one last example to take a look at. This is a slightly different flavor that we've seen from the other ones, but I think it's important to take a look at. So let's look at number 6. All right, question number 6 says, the base of the solid is defined by a circle. So we have a different shape this time. It's not our square root of x and our negative square root of x anymore. It's a circle, and they give us the equation right here. X squared plus y squared equals 1. Now the cross sections by planes perpendicular to the y-axis, okay, so that's different from last time. is perpendicular to the y-axis between x equals negative, or y equals -1 and y equals 1, and these are isosceles right triangles. So let me go ahead and draw my more regular looking graph. Okay, so I've got my xy plane. I'm going to draw the base in black to match the picture to the left, but I know that's different from the other videos. So I'm going to go ahead and draw that circle. Okay, and then let's look at how the bases are. So these bases are right here. They are perpendicular to the y-axis. That means my base does not go like that. That's not perpendicular to the y-axis. But my bases go this way. Okay, so that's one base of the isosceles right triangle. All right, it is the base of the isosceles right triangle. Now, if I were to draw a few more bases, like here, and even a tiny one up here, I would see that I'm stacking them up the y-axis, or that they're perpendicular to the y-axis. So unlike the other examples I've done, I want to do dy, not dx. All right, so let's set this up. The volume equals the integral from C to D of the area, and this time we'll seal it off with a dy. Now what that means is I'm going to need to know my y values, because that's going to be my bound. So this y value, they tell us, is -1, and this y value at the top is y equals +1. And so what I have are my bounds. So the integral from -1 to +1. Now let's talk about the area formula for an isosceles right triangle. So that's going to be 1/2 the base times the height dy. All right, so my base in this one is going to be this half plus this half, or 2 of one of the halves. Okay, now I need to find an equation that represents that, and I'm going to get that from here. Now I need to do a little bit of work for this, and if you remember from area between curves, if I have a y here and these are y numbers, then my equations here have to be equations with y's. So not like a 2x minus 7, but like a y plus 8. All right, so it should be an equation with a y in it. So we're going to take our equation and we're going to solve for x so that we get an equation with y in it. And then we're going to take the square root. Okay. So this equation right here actually tells us the definition of the right side of the circle, or that curve. But that also tells us this distance right here. And so I need to double this distance to be the base. So 1/2 comes out to the front, the integral from -1 to 1. The base is 2 root 1 minus y squared. And this is an isosceles triangle. That means the base and the height are the same, so I get to just double dip and write that same equation again for the height. All right, let's simplify. I know that this 1/2 and this 2 cancel, so I'm going to bring this 2 all the way out to the front. And then square root of 1 minus y squared times the square root of 1 minus y squared is just 1 minus y squared. All right, let's integrate. Y minus 1/3 y cubed, plugging in 1, plugging in negative 1. All right, 2 times 1 minus 1/3 times 1 cubed minus 2 times negative 1 minus 1/3 times negative 1 cubed. All right, so let's distribute 2 minus 2/3. Let's distribute plus 2 minus 2/3 is going to give me 4 minus 4/3. And let's convert to a common denominator. So 12/3 minus 4/3 is going to give me a volume of 8/3. All right, and so 8/3 represents the volume of the solid that has cross sections of isosceles right triangles inside of that circle. All right, folks, so I hope this practice explanation was helpful. The answer key is also posted on Canvas, so you can check that out. And I will talk to you soon. Bye.